You pulled dinner out of the oven without thinking twice about what actually happened to the food inside it. Heat changed it, made it softer, easier to chew, easier to digest. You do this every single day and never once consider that this small act might be one of the reasons you have the brain you have right now. Fire itself came earlier than cooking, and for a long time it was used mainly for warmth, for keeping predators away, for light in the dark after the sun went down. But at some point, your ancestors started putting food into that fire on purpose. And that decision may have done more to shape the human body than almost anything else that happened next. Biological anthropologist Richard Wrangham of Harvard University spent decades building what is now called the cooking hypothesis. His argument is direct. Cooked food is dramatically easier for the human body to break down and absorb than raw food. Heat unwinds proteins, ruptures the tough cell walls in plants, and turns hard, fibrous meat into something soft enough to chew in a fraction of the time. Wrangham proposed that this shift did not just make meals more pleasant, it freed up a staggering amount of energy that a raw food body would have spent on digestion, energy that could instead go toward growing and running a larger, more expensive brain. That claim needed testing, and in 2011, Wrangham teamed up with biologist Rachel Carmody, also at Harvard, to find out exactly how much energy cooking actually saved. Carmody's team fed mice diets of raw meat, raw starch, and cooked starch, then carefully tracked how much usable energy each mouse actually extracted from its food. The results were striking. Mice on cooked diets gained significantly more weight and extracted more net calories than mice eating the exact same raw ingredients, even though the raw and cooked versions contained identical amounts of energy on paper. Cooking was not just convenient. It was, in a very literal sense, unlocking calories that raw food kept locked away. Unlocking those calories meant your ancestors' bodies no longer had to work as hard just to break food down. Consider what that actually required physically. In 2016, biological anthropologists Catherine Zink and Daniel Lieberman, again at Harvard, studied how much chewing effort different food preparation methods demanded. Using volunteers eating raw goat meat, raw vegetables, and versions of the same foods that had been sliced, pounded, or cooked, Zink and Lieberman measured chewing force and the number of chews needed per meal. Cooking meat alone cut the number of chews needed by about 20%. Combine cooking with basic slicing or pounding, and the reduction in chewing effort became even larger. Over a single day, that difference adds up to hours of time and enormous amounts of muscular effort that a raw food ancestor would have spent just working their jaw. Less chewing was only part of the story. Digestion itself is expensive tissue to run. In 1995, anthropologist Leslie Aiello and physiologist Peter Wheeler proposed what became known as the expensive tissue hypothesis. Comparing humans to other primates, they found that the human gut is unusually small relative to body size, while the human brain is unusually large. Both organs are metabolically costly to maintain, burning energy simply by existing, whether or not they are actively being used at any given moment. Aiello and Wheeler argued that a smaller gut could only have evolved safely alongside a higher quality, easier to digest diet, since a shrinking digestive system needs less raw processing power to extract the nutrients a body requires. Cooked food, softer and already partly broken down by heat before it ever reaches the stomach, fits that requirement almost perfectly. In their model, the shrinking gut and the growing brain were not separate coincidences. They were connected, made possible in large part by a diet that no longer needed a large digestive system to handle it. Picture what a raw diet actually demanded. Modern great apes like chimpanzees spend nearly half of every waking day chewing tough raw plants and meat, jaw muscles working almost constantly just to get enough calories to survive. Now picture an early human ancestor sitting beside a fire instead, spending a fraction of that time eating a cooked meal, then walking away with hours of the day still open. That extra time and that extra energy had to go somewhere. Researchers like Wrangham argue it went toward exactly the traits that make humans distinct. Larger brains, smaller jaws and teeth, shorter guts freed from the burden of processing tough raw material, and more time available for tool use, socializing, and the kind of long, complex childhoods that let humans learn so much before adulthood. Think about what that freed up time might have actually looked like on the ground. Day after day, season after season, a chimpanzee that spends most of its waking hours chewing has very little time left for anything else, no matter how clever it might otherwise be. An early human sitting by a fire after a cooked meal, by contrast, had spare hours that could go towards shaping a better stone tool, teaching a child which plants were safe to eat, or simply resting long enough to think clearly about tomorrow's hunt. None of that required a bigger brain on its own, but a bigger brain, once it had the spare calories to grow and the spare time to be useful, had a much better chance of actually paying for itself. This was not limited to modern humans either. In research on Neanderthal dental calculus, the hardened plaque preserved on ancient teeth, archaeologist Karen Hardy of the University of York and ICREA identified microscopic starch granules that showed clear signs of having been cooked before they were eaten. Some of these granules came from plants Neanderthals would have had to actively seek out, process, and heat, not simply chew raw off the stem. That evidence suggests cooking was not a uniquely modern human habit picked up late in the story. It stretched back into a closely related branch of the human family tree as well, embedded deeply enough in the behavior of ancient hominins that it likely predates the split between Neanderthals and modern humans altogether, meaning the habit of heating food before eating it may be older than our own species itself. Here is the twist worth sitting with. It would be easy to assume that cooking was simply a matter of taste, that ancient people started heating food because it tasted better once they discovered fire could do that. The evidence points to something with far higher stakes. A body that extracts more calories with less digestive effort has more energy left over for everything else that energy could possibly build. Brains are extraordinarily expensive tissue, burning a disproportionate share of the body's total calories just to exist. Without the extra fuel that cooking freed up, there may simply not have been enough energy available to grow and sustain a brain anywhere close to the size yours is today. Cooking may not have followed human intelligence. It may have helped make human intelligence possible in the first place. You pulled dinner out of the oven without thinking twice about what actually happened to the food inside it. That small, automatic act connects you directly to a decision your ancestors made around a fire hundreds of thousands of years ago. A decision that traded hours of exhausting raw chewing for a softer meal, and quite possibly for the extra energy that helped build the very brain you are using to read these words. Every time you soften a vegetable in a pan, tenderize a cut of meat, or simply let something simmer until it falls apart easily on a fork, you are repeating the same basic trade your ancestors made long before anyone wrote anything down. Less effort spent breaking food apart with your body, more energy left over for everything else a body and a brain like yours can do with it. If stories like this one make you see your own everyday life differently, hit subscribe. A new story from the deep past goes up every week.